For logistic regression, we previously talked about two types of optimization algorithms. We talked about how to use gradient descent to optimize this cost function j of theta, and we also talked about advanced optimization methods, ones that require that you provide a way to compute the cost function j of theta and that you provide a way to compute the derivatives. In this video, we'll show how you can adapt both of those techniques, both gradient descent and the more advanced optimization techniques, in order to have them work for regularized logistic regression. So here's the idea. We saw earlier that logistic regression can also be prone to overfitting if you fit it with a very sort of high order polynomial features like this, where g is the sigmoid function, and in particular you may end up with a hypothesis whose decision boundary is this sort of a overly complex, extremely contorted function that really isn't such a great hypothesis for this training set. And more generally, if you have logistic regression with a lot of features, not necessarily polynomial ones, but just with a lot of features, you can end up with overfitting. This was our cost function for logistic regression, and if we want to modify it to use regularization, all we need to do is add to it the following term plus lambda over 2m, sum from j equals 1, and as usual, from 1, sum from j equals 1 rather than sum from j equals 0 of theta j squared, and this has the effect, therefore, of penalizing the parameters theta 1, theta 2, and so on, up to theta n from being too large. And if you do this, then it will have the effect that even though you're fitting a very high order polynomial with a lot of parameters, so long as you apply regularization and keep the parameters small, you're more likely to get a decision boundary that maybe looks more like this and looks more reasonable for separating out the positive and the negative examples. So when using regularization, even when you have a lot of features, the regularization can help take care of the overfitting problem. How do we actually implement this? Well, for the original gradient descent algorithm, this was the update we had. We would repeatedly perform the following update to theta j. This slide looks a lot like the previous one for linear regression, but what I'm going to do is write the update for theta 0 separately. So the first line is my update for theta 0, and the second line is now my update for theta 1 up to theta n, because I'm going to treat theta 0 separately. And in order to modify this algorithm to use the regularized cost function, all I need to do is pretty similar to what we did for linear regression, is actually to just modify this second update rule as follows. And once again, this cosmetically looks identical to what we had for linear regression, but of course is not the same algorithm as we had, because now the hypothesis is defined using this. So this is not the same algorithm as regularized linear regression, because the hypothesis is different. Even though this update that I wrote down, it actually looks cosmetically the same as what we had earlier when working out gradient descent for regularized linear regression. And of course, just to wrap up this discussion, this term here in the square brackets, so this term here, this term is of course the new partial derivative with respect to theta j of the new cost function j of theta, where j of theta here is the cost function we defined on the previous slide that does use regularization. So that's gradient descent for regularized linear regression. Let's talk about how to get regularized linear regression to work using the more advanced optimization methods. And just to remind you, for those methods, what we needed to do was to define a function that's called the cost function that takes as input a parameter vector theta. And once again, in the equations we've been writing here, we use 0 index vectors. So we had theta 0 up to theta n, but because octave indexes the vectors starting from 1, theta 0 is written in octave as theta 1 is written in octave as theta 2, and so on down to theta n plus 1. And what we needed to do was provide a function called cost function that we would then pass into what we saw earlier. We would use the f min u and c, and then at cost function and so on, right? But the f-min UNC was the f-min unconstrained, and this was what would, and f-min UNC was what would take the cost function and minimize it for us. So the two main things that the cost function needed to return were first jval, and for that we need to write code to compute the cost function j of theta. Now when we're using regularized logistic regression, of course the cost function j of theta changes, and in particular now our cost function needs to include this additional regularization term at the end as well. So when you compute j of theta, be sure to include that term at the end. And then the other thing that this cost function thing needs to provide were the gradients. So gradient 1 needs to be set to the partial derivative of j of theta with respect to theta 0. Gradient 2 needs to be set to that, and so on. And once again, the index is off by 1, right, because of the indexing from 1 that Octave uses. And looking at these terms, this term over here, we actually worked this out on the previous slide. It's actually equal to this. It doesn't change because the derivative for theta 0 doesn't change compared to the version without regularization. And the other terms do change, and in particular, the derivative with respect to theta 1, we worked this out on the previous slide as well, is equal to, the original term and then minus lambda over m times theta 1. Just so we make sure we pause this correctly, if we can add parentheses here, right, so the summation doesn't extend. And similarly, this other term here looks like this with this additional term that we had on the previous slide that corresponds to the gradient from the regularization objective. So if you implement this cost function and pass this into f-min UNC or to one of those advanced optimization techniques, that will minimize the new regularized cost function j of theta, and the parameters you get out will be the ones that correspond to logistic regression with regularization. So now you know how to implement regularized logistic regression. When I walk around Silicon Valley, I live here in Silicon Valley, there are a lot of engineers that are frankly making a ton of money for their companies using machine learning algorithms. And I know we've only been studying this stuff for a little while, but if you understand linear regression, logistic regression, the advanced optimization algorithms, and regularization, by now, frankly, you probably know quite a lot more machine learning than many, certainly not all, but you probably know quite a lot more machine learning right now than, frankly, many of the Silicon Valley engineers that are out there having very successful careers, making tons of money for the companies or building great products using machine learning algorithms. So congratulations, you've actually come a long ways, and you actually know enough to apply this stuff and get to work for many problems. So congratulations for that. But of course, still a lot more that we want to teach you, and in the next set of videos after this, we'll start to talk about a very powerful class of nonlinear classifiers. So whereas linear regression, logistic regression, you can throw in polynomial terms, but it turns out that there are much more powerful nonlinear classifiers that can than sort of polynomial regression. And in the next set of videos after this one, I'll start telling you about them so that you have even more powerful learning algorithms than you have now to apply to different problems.